Okay. All right, so in order for a function to be differentiable at a point, x equals a, first of all, f must be continuous at x equals a. Okay? So, first of all, you must prove continuity. However, you may do that with the particular graph. Then, you must show that the derivative from the left equals the derivative from the right. So, let's use this limit definition of a derivative. Yes. Slope at 1 point.
So, how is there a left and right side of the
Like if you're approaching from the left or approaching from the right. So, for example, let me finish writing this and I'll tell you.
That says that the point is not instantaneous, but it's a range.
So, what is the difference between what I've written here twice? Left side, right side here. All right. Yes. More or less, yes. But we're dealing with derivatives instead of just continuity. Yes.
So you're pretty much saying
So this more or less is the derivative from the left I was way too late for that. Yes. Yeah, continuous is going to be the same as we've been doing for being continuous. And then we have to look at the limit definition from the left and from the right. So derivative gives us slope. So like here, slope from as you approach from the left, slope's -1 everywhere until you get to this point. And then here, slope's +1. So since those two do not equal, you're not differentiable at that point. All right, let's do an example. Yes, differentiability on top of it. Yes. Yes, we'll take some paper. Yeah.
And then she's going to give us like 20 questions.
The derivative, if you're thinking about the graph, is the slope at that point. Yes, we will be talking about at one single point. Now, if you're given like a function, like if you're given f prime of x equals x plus 2, or like whenever you found the derivative on some of your homework, and your answer was 2x plus 5 instead of being like a number, that was the derivative at any point. But if you wanted to know at a single point, you just plug that number in. But you won't need to do that here, so let's not worry about that right now. That's not totally related. Yes?
So
Okay? Alright, so, alright, let's do this one so you see what you're going to have to do for this. So, if we're thinking about what we've got here, this is a line, this is a quadratic. They are both continuous for their domains. They're both going to be differentiable because they're just lines. They're not going to have sharp turns, right? Where would we have a sharp turn if we're going to have a sharp turn? At 0, right? That's our issue. So 0 is where we need to figure out if this is differentiable or not. So we first have to do continuity. We've done continuity before. So continuity is just the limit as x approaches 0 from the right of f of x. This is continuity, not differentiability so far. Right? So from the, actually let me do the left first. Just like to organize it that way a little better. So we would just plug in 0 into the function from the left, which is our top function here. So that'd be 0 plus 1, which would give us 1. Right? We will do the limit as x approaches 0 from the right of f of x. Right, we're not doing derivatives yet. We're just proving continuity, which we've done before. So this would be 0 plus 1 squared, which also equals 1. What else do I have to consider for continuity? F of 0 also equals, in this case, 1, right? Because it's just the same as the limit from the left. It doesn't have to if it has like, or no, it does have to be continuous. Yes. For the limit to exist, it does not have to, but to be continuous, it does. Yeah. All three of these have to be equal to each other. So we could say, therefore, f is continuous at x equals 0. So f is continuous here. Okay, so continuity, you're just essentially, you're plugging in to both of these and making sure they're the same. You're going to use this limit notation as you do it.
Wait, so that's what I need to do. Is that what we did?
Okay, so this is continuity. Are there any other questions on continuity before we move on to?
I can't put them in words.
We're not done. We're not done. This is, we must show that this is continuous before we can do differentiability. So this is continuous. So now we need to work on differentiability. So for differentiability, I'm going to write this down again. The limit as x approaches, in this case it's going to be 0 from the right of f of x minus f of 0 over x minus 0. Right? So the limit, actually I like doing the left first. Let me change it to the left. Left equals the limit as x approaches 0 from the right of f of x minus f of 0 over x minus 0. Okay, that's our limit definition of a derivative at a point. I'm using that one instead of the x plus h. You could use the x plus h, but this just lends itself to being a little bit easier.
You know that the picture of that dude from The Simpsons where he's sitting on the bus and he's laughing, saying, "I'm in danger."
All right. We're not going to use x plus h on this one. I was saying we're using limit definition of a derivative at a point, which is the limit as x approaches a of f of x minus f of a. This is the first one that we did.
That means nothing.
This is limit definition of a derivative at a point.
Wait, so then you choose not to use that?
Wouldn't that be like?
You could use x plus h, but if you use x plus h, it makes it a little bit longer for these problems.
So Does f of x
Okay, so from the left, what is our f of x? X plus 1. Okay? So we got the limit as x approaches 0 from the left of x plus 1. What was f of 0? 1. From the left, it's going to be 1 over just the x right here. So x approaches 0 from the left. You're going to have the 1's cancel, which just gives you x over x, which is just 1. So you just get 1. Actually, let me work down instead of across. Okay. So from the right, my f of x does not equal x plus 1. What does it equal? X plus 1 squared minus, what is f of 0? It should be 1 all over x. And so here, I've got to expand this. I've got x squared plus 2x plus 1 minus 1 over x. So these will cancel, which gives me, I've got x squared plus x plus 2x. What could I do right there? Factor out of x. X times x plus 2 over x. My x's cancel. So I've got 0 plus 2, which equals 2. Does 1 equal 2? No.
So that's basically.
Therefore, f of x is not differentiable
Basically a sharp.
at x equals 0.
So there's a little bend in the graph right here.
Yeah.
Sharp.
Yeah. Mm-hmm.
How are we taking the limit of the derivative at a single point?
That is what I have been asking.
This formula right here, just where you're plugging in the a, that is going to be the single point. So this, it's kind of like doing the x plus h definition and then plugging in that number. So you could do it this way where you use the x plus h definition, but you would have to plug in 0 at the end. Right, and it like automatically plugs in the number. Right, you don't have to do the x and h's, which usually is a little bit longer, which is why I chose to use this. Well, not forever, but yeah, for this. Yeah, so if we look at this, let's look at this on Desmos.
So we're finding the slope at one point based on other points that are not given to us. Correct.
Guys, this is not that hard. You're overthinking it. Yeah. So if you look at this graph right here, right? So you got the line on the left. You got the blue graph on the side here. So in order for this to be differentiable, it has to be a smooth curve. Now this is not a really sharp turn, but it's not smooth either. Like the more that we zoom in, we can kind of see. I don't know, zooming in might make it worse. But it's not, it does not look like a perfectly straight line there. Whereas if I, like for example, I can't make up on this. But like, if you pick another point, it's not a straight line right here either. But if I zoom in enough, it starts to look like a straight line. So if you have even like the least little bit of a sharp turn in the graph, then your slope from the left does not equal your slope from the right, so you're not differentiable at that point. Right. We want to see, so if we had one where the slope on the left was 1 and the slope on the right was 1, it would make like a smooth transition. Okay? Derivatives equal the same with the left and the right, yes. What? So at this particular point, we have 2 because we've got 2 different functions coming together. So you would not use this for you would mostly use this for piecewise functions. You would not use this for like a quadratic or a cubic or something like that. So it would only be where you've got 2 coming together and you want to see if they have the same slope from the left side and the right side.
I'm not really understanding how there's different sides of one point.
So if you are approaching this point, because we're talking about this point right here, if you approach it from the left, then you're on that red line right there, the x plus 1. So as you get closer and closer and closer and closer and closer to that point, right, but you get infinitely close to it, which is what our limit definition tells us to do. Right, and because, yes, exactly. And then so from the right, you approach, you're on that blue line the whole time as you get infinitely close. Yeah. Okay. All right, so let's look at this really quickly. Let f be the function defined above. Which of the following statements is true? Okay, so we need to know if it's differentiable or not. In fact, all of these say it's not differentiable, so I'm going to guess it's not differentiable.
I didn't read the answers.
So, alright, so if I plug 5 in here, since this one's a multiple choice, I'm not going to go through the whole showing every step. But if I plug in here, then I get 2. If I plug in over here, I do 2 times 5 minus 4. 10 minus 4 gives me 6. Is this continuous? The slope is actually the same on both points. But it's not continuous. Because right now I'm just plugging into the equation. Oh, no, I'm sorry. You're right. It's not got the same slope. You're right. Sorry. I was treating it like there was an X right there. So, this is not continuous, though. So, f is not differentiable because it's not continuous. Okay?
I don't like how you circled it.
Why did you fill it in?
Okay, look at this really quickly. Which of the following statements, if true, cannot be used to conclude that f of 0 exists?
D.
It's A. Why is it A? Do you still have a limit? Yeah, you still have a limit even if you have an open circle right there. But to be continuous, that's got to be filled in. And it's got to be, you know that if it's differentiable, it's continuous. So, yeah, you can have a limit without being continuous. So f of 0 does not have to exist.
So literally, it's true because the answer is the question.
Maybe. So for the limit, you can have for the limit, you can have an open circle here, which would mean that point does not exist. And this says it cannot be used to conclude that it does exist. So we could know the limit exists, but it doesn't necessarily mean that f of 0 exists.
Because it's that one little point.
Right.
It doesn't really matter. But
Right.
everything else is going up.
Right. Okay.